Okay, let's just dive right into this. Every single time you load a web page, shoot off an email, or stream a video, there's this massive, invisible symphony of digital communication happening literally right beneath your fingertips. I mean, it kind of feels like magic, doesn't it? But actually, scratch that. It isn't magic at all. It's a highly structured, brilliantly engineered set of rules. So welcome to this explainer. Today we're going to demystify the absolute backbone of our entire digital world, the TCP/IP protocol suite.
So here's our quick roadmap for today. We'll start with the Universal Internet Language, then look at DARPA and its early origins, move on to designing the protocol suite, dive into the TCP three-way handshake, and finally wrap up with evolution and modern challenges.
Okay, Section 1, the Universal Internet Language, the backbone of the Internet. Before we really get into the nitty-gritty of how it works, we need to establish exactly what it's doing for us on a global scale. At its core, TCP/IP stands for Transmission Control Protocol and Internet Protocol. Basically, it's a suite, a collection of protocols that acts as the universal language of the Internet. Think about the sheer variety of devices out there, right? You've got smartphones, laptops, massive cloud servers, and they're all running different operating systems on totally different networks. Well, TCP/IP is the foundational layer that bridges all of them together. It provides the standardized rules for exchanging data, allowing completely disparate networks to communicate seamlessly. Honestly, without it, the Internet as a globally connected entity simply would not exist.
Now, to give you a real idea of the immense importance and, frankly, the sheer complexity of this subject, just take a look at this quote. This is a review written by network engineer Robert A. Ciempa for the incredibly famous book TCP/IP Illustrated. He wrote, "This is sure to be the Bible for TCP/IP developers and users. Stevens reveals many of the mysteries once held tightly by the ever-elusive networking gurus." I just love this quote because it really hits the nail on the head. For a long time, the way the Internet actually routed our data felt like an elusive mystery, even to the professionals. And in this explainer, we're going to show you the tip of that exact same iceberg. Moving on to Section 2, DARPA and Early Origins, how it all began.
So where did this all come from anyway? Let's take a quick step back to see the macro-level problem early computer scientists were desperately trying to solve. Back in the late 1960s, the Defense Advanced Research Projects Agency, or DARPA, funded ARPANET. This was literally the world's first operational packet switching network. But they ran into a major problem. Their initial communication protocol, which was called the Network Control Program, or NCP, well, it just wasn't scalable or robust enough. They needed a communication method that could actually survive severe network disruptions or node failures. Enter two visionary scientists in the early 1970s, Vint Cerf and Bob Kahn. These guys collaborated to design a revolutionary new protocol suite to replace NCP. And, their work was so profoundly effective that by 1983, ARPANET officially adopted TCP/IP as its operational backbone. That moment basically heralded the dawn of the modern Internet.
All right, Section 3, designing the protocol suite, form and function.
We know history required a robust solution, right? So how exactly did Cerf and Kahn design the form and function to pull that off? Well, the absolutely crucial point here is this two-layer abstraction they created. Honestly, it was a strategic masterstroke. They completely separated the duties. On one hand, you have the Internet Protocol, or IP, which is purely responsible for handling data packet routing. Its only job is to get the packet from address A to address B. Simple enough. Then, layered right on top of that, you have the Transmission Control Protocol, or TCP, which manages the actual reliability of that transmission. By separating the routing from the reliability, they introduced a level of abstraction that just massively enhanced the flexibility of network communications.
Now, to truly understand why TCP is so special, we have to contrast it with another transport layer protocol called UDP. You see, applications actually choose between these two based on their specific needs. UDP is incredibly fast, but it's unreliable. It's very much a fire and forget kind of system. If a packet gets corrupted, UDP just tosses it out. And hey, that's totally fine for super quick tasks like DNS lookups. But TCP? TCP is completely different. It ensures strict reliability using a system called Positive Acknowledgement with Retransmission, or PAR. With TCP, every single segment sent absolutely must be acknowledged by the receiver. If it gets lost, or if the checksum detects any corruption, the sender automatically retransmits it. So, TCP guarantees your data gets there perfectly intact, no matter what.
Which brings us to Section 4, the TCP three-way handshake, machines having a conversation.
Okay, we're zooming all the way down to the micro-level mechanics now. Before any data can be transferred reliably, these machines have to actually establish a connection.
It is quite literally the digital equivalent of two polite people setting up a phone call. But before our machines can talk, we need to know exactly what they're passing back and forth. Basically, TCP encapsulates the data bytes with a header that ranges from 20 to 60 bytes. This header contains the source and destination ports, sequence numbers for ordering, and acknowledgement numbers. But what I want you to pay really close attention to are the control flags at the bottom: SYN, AK, FIN, RST, PSH, and URG. These one-bit flags act as the specific signals that dictate the entire state of the connection. And for our upcoming handshake, the SYN, or synchronize, and AK, or acknowledge, flags are totally the stars of the show.
Now, what's really interesting about this is just how perfectly logical and, well, human-like this whole process is. Let's walk through the famous three-way handshake in 3 simple steps. Step 1. The client reaches out to the server. It sends a segment with the SYN flag set. In human terms, the client is basically saying, "Hello, I'd really like to talk, and here's the sequence number I'm starting with." Step 2. The server receives this and responds by setting both the SYN and ACK flags. So now the server is saying, "I hear you, hello, I acknowledge your sequence, and here's my own sequence number to start our conversation." And finally, step 3. The client sends a segment back with just the ACK flag set. Loud and clear, "I acknowledge your sequence, let's talk." And boom, just like that, a perfectly reliable connection is established. An actual data transfer can finally begin.
Let's wrap things up with Section 5, Evolution and Modern Challenges, zooming back out.
So, we've seen the history, we've explored the design, and we just unpacked the micro-level handshake. Now we really need to zoom all the way back out to understand the massive scope of this technology today. This perfectly illustrates the true scale of what we're talking about. Remember the cover of TCP/IP Illustrated Volume 1 we mentioned earlier? We just spent some time deeply understanding the three-way handshake, which is absolutely crucial for sure. But I want to make one thing crystal clear. That handshake is merely the tip of a colossal digital iceberg. I mean, a massive textbook like this exists because the protocol suite is just staggering in its depth.
Just look at this rapid-fire list derived from the vast components that make up the whole TCP/IP ecosystem today. You've got the link layer and incredibly complex IP routing tables. You have ARP for address resolution and DHCP, which automatically hands out IP addresses so you don't have to configure them manually. You've got firewalls and network address translation, or NAT. You have the domain name system, DNS, which is out there translating human words into IP addresses. And on top of all that, you have massive layers of security bolted on, like IPsec, TLS, and DNSSEC. Okay, I'm playfully overwhelming you with this list on purpose, because the point is, TCP/IP isn't just one single thing. It's literally the entire infrastructure of modern digital society.
And because it is the infrastructure for literally everything, it has to constantly evolve just to survive its own success. You know, throughout the 80s and 90s, internet adoption saw this exponential, wild growth. So much growth, in fact, that we literally ran out of initial IPv4 addresses. Because every single device needs an address, a 32-bit system just wasn't enough to cover the whole planet. So what did they do? The Internet Engineering Task Force standardized the introduction of IPv6. By expanding the address space from 32 bits to a massive 128 bits, they didn't just solve the address exhaustion problem, they also introduced much better built-in features for security and configuration. It's just a perfect example of how the suite naturally adapts to keep the internet alive and kicking.
Which ultimately leaves us right here. The foundational design principles of openness, scalability, and robustness that Vint Cerf and Bob Kahn baked into TCP/IP way back in the 70s have ensured its relevance for half a century. But as we transition into an era powered by ultra-fast 5G networks and literally billions of new Internet of Things devices coming online, we have to ask ourselves, how will the underlying principles of TCP/IP continue to adapt to secure and support the next generation of human innovation? It's a completely fascinating question, and it's one that the global technical community is working on right this very second. I really hope this explainer gave you a deep appreciation for the invisible magic connecting your world. Until next time, keep learning and keep exploring.